cool thing about this particular theorem is that the converse actually is true. So the converse of this theorem also holds, which means that if you have this figure like this, but you're not sure at this point that this line EF is parallel to BC, but all you know is that you have this is to that as this is to that, then we can conclude that these two lines are parallel. So in fact, the converse holds. If in fact you have a line that divides two sides proportionally, then in fact that line is parallel. So that's pretty a cool fact that comes in handy. In fact, it comes in handy right now. Let's take a look at this picture where we have a tiny, tiny, tiny triangle right here and a larger triangle here, and we're wondering if in fact this line segment AE is parallel to BD. That's the question. Well, let's see if in fact we have a proportion that holds. So let's take a look and see. This is to that, so that's 44 is to 11. Well, that works out to be 4. And how does that compare to this is to that? 36 to 9. Well, that also equals 4. So I see they're equal. So in fact, this is a proportion. And since it's a proportion, by the converse theorem, I know that these two sides are parallel. So the theorem and its converse both hold, and we can use it in this case. Terrific.